Okay, welcome everyone. This is our last talk for today. We have Quang Dao from CMU. He's going to be talking to us about VCVio. So, Quang can also hear our questions, so feel free to raise your voice if you need to ask Quang something. All right. We are keeping this informal. Yeah, Quang, whenever you're ready. Thank you.
Yeah, thank you so much. So very excited to be talking about VCVio today with all of you. This is work that's been done. I think it was started by Devin all the way back in 2021, 2022, and then I joined about 2 years later, and we've been building this ever since. And especially in the recent months, we've had a lot of progress. We've made a lot of progress with AI. And so I'm going to talk a little bit about that at the end of the talk. But first, this talk is really about laying out what VCVio is, how we approach the question of formally verifying cryptography, and the sort of insights that I think we've learned along the ways. So yeah, let me try to, okay. So let me just start here by sort of reminding ourselves why we're in this workshop. So we are interested in formally verifying Signal. And Signal is a complex cryptographic protocol. And it has all the reasons for why verifying crypto is so difficult. For one, these protocols, they are not just deterministic programs. They're stateful, probabilistic, they interact with each other, there are many parties, and you have to handle adversarial corruption. The proofs about, say, protocols, for example, signals, they are oftentimes, if someone manages to formalize them, the proofs are very difficult. Oftentimes, though, the proofs are even informal or non-existent at all for the security of the protocol. And if you want to really have an end-to-end guarantee, then you have to bridge two very different worlds, one coming from very abstract math, and the other one is very low-level semantics of the ISA that you are compiling to. And finally, I think this is something that we always have to keep in mind, which is that the formal models, the things that we formally verify, are usually always catching up with what's actually deployed, what's actually out there. And so there's going to be potentially bad cases where we don't document the verification boundaries very well, and that leads to gaps in the formalization. So I'm sure all of these problems are familiar to all of you today, but I just want to go over them again in motivation for the tools that cryptographers and people in the formal verification community have built over the years. So this is really a very non-exhaustive list of tools. I just want you to show you the states of the field very roughly. And what we have is we have a lot of tools that can be classified in many different aspects. You could talk about whether a tool is working in the symbolic model or the computational model, whether that means the tool is foundational, meaning it relies on a very small trusted computing base, such as a general theorem prover like Lean or Rock. You can also talk about what kind of program logic is supported, what kind of automation and tactics are available, and there are lots of tools with lots of achievements over the years. So here I'm just giving you all of this, and what I want to point out is a rather, I think, sharp transition between two eras. The eras are before the AIs that we know today exist and after AIs exist. Perhaps this line can be a little blurry. I don't mean it to be exactly like this, but roughly speaking, I think in both VCVio and in CACrypt, we're now depending heavily on AI to speed up our work. And that can lead to very drastic effects. Okay, so right. So catcrypt, I'm sure you've heard from Bas this morning, and I hope that the code can be available soon. But for the purpose of today, I will focus on VCVio, and if there are any questions from the audience on how that compares to catcrypt, I will be happy to answer based on my limited knowledge. Okay, so VCVio, the name itself, it's sort of a there's some trivia about the name, but I'll leave that later. It's basically, it's one way you could think about it is verify cryptography via index computations, and the index computation or index oracles part is really the core of what this framework is hoping to build. The core observation that we started from is that cryptography depends on oracle calls. You need that oracle calls to, say, sample randomness, perform hashing, interact with other parties, and all kinds of things. And in reductions, we also do all kinds of things with these oracle calls. You can intercept them, you can reroute them, you can do all sorts of things with them. Okay. So that's the starting point. Along the way, we sort of developed a few, I think, design principles for what we are hoping to accomplish. One of them is that we want this to really be as minimal as possible, but also as extensible as possible. But it also means that we don't want accidental complexity when it is not needed. And the way that we went about doing so is that we look at established literature in PL theory, category theory, and previous formal verification literature with a lot of previous tools. There's a lot of knowledge there and inspiration and insights that we build upon. So the core abstraction that we came to is that there is an almost perfect correspondence between handling these oracle calls and oracle semantics and the theory of algebraic effects and handlers. So if you don't know about what algebraic effects and handlers mean, it doesn't matter so much, because I'll show you precisely what it is. Okay. So the most general modeling that exists, not just for cryptography, but also for PL in general, is that of free monads as describing sort of uninterpreted computations. And precisely the kind of free monad that we talk about is that you have a computation that can query an oracle set that is indexed by this iota. And for each value of iota, you may have a different response type. So given such an oracle specification, you can have an oracle computation that at every step either does a pure, or it either returns, or it makes a query and then it specifies what it will do when it gets the result. One very simple example is that of a probabilistic computation. Here, the oracle is that for every number, you can sample a number from 0 to n. And so that's just sort of a toy model, but one that we could keep in mind. So that is oracle computations. Technically speaking, free monads you can denote into anything. And in fact, we do take advantage of that, but we also just stack regular monad transformers on top of that. So for instance, this oracle computations, the way we denote it is usually that it doesn't fail. So if you want to add failure or exceptions, you can just add it with monad transformers. That is one of the ways we can deal with this, but there are also other ways as needed. So here is just, for instance, this is what a Rust program, when translated through HAX or through ANIAS, will denote into our system. Okay, so that was just oracle computations. what about handling Oracle queries? Well, so here, a handler is really just a mapping from the index into a computation that returns a response of that of the corresponding type, and the computation can range over an arbitrary monad, and this is really the universal properties of free monads. So given this, we can run an Oracle computations by interpreting this query handler or query implementations. And it goes the way that you expect. You get the implementation, you run it, you get the result, and then you continue with the rest of your work. Okay, and already using this, we can have a lot of useful handlers that we use all the time. So I'm just going to show some of them here today. One of them is for tracing. Say you can accumulate your result to some monoid omega. This monoid can be either used for logging Oracle queries, for counting how many queries you make, which is very useful also when you try to count for the cost of adversaries and reductions. And it can be used for other things as well. Beyond just logging or tracing, we also have stateful effects. So for instance, a random oracle in a lazy format, you would usually, when you get a query, you would either see if it's already been queried before. In this case, it would land in the cache, and then you just return the cache. Or if you don't find it in the cache, then you would sample a fresh query, and you would sort of cache that query with this function update, and then return that result. And note here that this is really a transformer on handlers themselves. You can have a query implementation, an arbitrary base query implementation, and then you can just lift that with these extra tracing or caching effects. So it's very compositional. And everything, again, flows out of very established and well-known theory on free monads and the universal properties of free monads. Okay. Now, the next step is, how do we actually interpret these Oracle computation? And how do we reason with programs that we write using Oracle comps? So the first step here is that we need to find a way to denote that into, say, the type of probabilistic computations, either with or without failures. And this is just a specific handlers that we provide. And the one that we provide is that, first of all, for Oracle computations, this is just a convention. So we say that assuming the spec, every response type in the spec is finite and non-empty, we can sample the response uniformly at random. And then once you run that with this effect, with this handler, then you have your probability mass function, the probability distribution that corresponds to an Oracle comp. You can very easily lift this to a sub-probability distribution on the Oracle comp that you then augment with possible failure. And this is just through mapping through this option T monad transformer. The point here I want to make also is that these classes, they are fairly general. So catcrypt, for instance, we can have a another instance just for these two classes, even if the two monads, the underlying monads, are very different. Okay. So that was in terms of semantics. What about actually reasoning with programs? And here we come to the very rich literature of program logics. The point here is that we want to be able to have powerful reasoning principles, especially for relating two Oracle computations with each other. They may have different specifications, they may have different return types, but as long as you can thread through some kind of relation between them, and in particular, the relation that we care about is coupling of two probability distributions, then we can start to reason about these programs. So the program logic that VCVio has right now is called ERHL. This is a recent work by several authors, and we embed it as the base logic. This recovers or is a generalization of the classic PRHL or probabilistic relational Haar logic. Okay, so I think so far here it's fairly standard. What we have on top of this is that we have a relational weakest precondition algebra that can lift the original relational weakest preconditions, or just oracle column, say without failure, without state, without exceptions, into richer monad transformer stacks on top of oracle column. And this work, I think the precise formulation is not, I haven't found it anywhere written like this precisely, but it is sort of a extrapolation from the very recent work of Loom with sort of older works on like general relational Haar logic. And here we have an extension. I'm not, I guess, just that I can't find this anywhere else just doesn't mean that I think this might be folklore in some sense. But anyways, this allows us to lift from one monad and the other into a sort of arbitrary monad transformer stacks on top of it. So let me just show you some examples. So for instance, you can lift this through option T on both sides. What this means is that when you do the relational coupling, if either of the programs happen to fail, then we would just return the lowest level on the truth logic, on the truth lattice, in which case this is the non-negative real numbers. You can also layer this with states, and then you have something that changes here, which is that the lattice of the truth is changed from the non-negative real numbers to actually functions over mapping into the non-negative real numbers, taking in both the states. Okay, and all of this is just generic from the general class. I think this is one of the design strengths of Loom, and we build upon that. Okay, so we have the semantics, we have the base program logic, but to really utilize this, we need to have lots of good tactics. So this is something that is ongoing work. The first thing that I want to note is that we can plug in to MVCgen, which is the current framework for reasoning about a imperative deterministic programs that is shipped with Lean right now. And this is something that I know Anias and Hacks also builds off of. So we can support that. We can plug into it for goals that are also deterministic. So this is, for instance, an example about the behavior of caching oracles. It roughly says that this is the preconditions. So if there's some cache that contains this initial cache, then when you execute this program, which basically do some caching oracle calls, then the initial cache will still be part of this cache C, and that after querying for T2, you would now have T2 in the cache. That's roughly it. Okay. Beyond this, though, we can't just rely on MVCgen because we have probabilistic goals, we have expectation-based goals, and we also have relational goals. So there is an additional layer of tactics on top that is actively under development that tries to extend MVCgen to these settings. So one of the things that we can do is that we can try to step through these programs. And when you step through these programs, you can also specify the precise coupling that is needed for the proof to go through. So all of this is, I think, our attempt to merge MVCgen with all the various tactics that EasyCrypt provides. And along the way, we can hope to improve upon the tactics framework that is already in EasyCrypt by sort of condensing them and consolidating them into a smaller number of good tactics, or very general tactics that can subsume many of the previous tactics that we have in EasyCrypt. I think there's going to... Yeah, of course.
Yeah, so you're using Loom for the more general kinds of monads that you have, and so you're using Loom's integration with MVC Gen. Are you
not
here that work on by Vova on that?
Yes, so I think that integration is still private right now, so that's why I can't really connect to it. But once it's public, I will start pouring to that framework.
Okay, nice.
Yeah,
We'll connect soon.
Soon. Okay, good. Here's a question.
Yes, thanks for the question. Yeah, but I think there's at least to me a lot of open questions on how to design these tactics in the best way possible to get the best sort of ergonomics for writing proofs, and importantly, writing proofs here not just for humans but also for AIs. I'll come back to this a bit later. Okay. So this is the state of basically the foundations of VCVio right now. And now I'll talk about applications or things that are built on top of this core framework. Okay, so the first case study I want to make is that of formally verifying proof systems, cryptographic proof systems that can be interactive and have all kinds of complex side effects. So, and this is done in the RClip library, which is jointly developed by many people, including Alex Hicks and Derek in the audience today. So in the setting, the core setting of RClip is that we formalize an object called interactive oracle reductions. This is an abstraction that is brought forward by the community in recent years, and we really flesh them out, and we fill in the gaps that proof writing on paper doesn't quite cover. So what this means exactly is that you have two parties, a prover and verifier. They interact with each other over a number of rounds. Importantly, is the structure of the protocol can actually be dependent. So for instance, the value of the message or of a challenge at one point can determine the type of message or the execution pattern of the rest of the protocol. This happens rarely, but it does happen when we actually encounter these protocols in practice. On top of that, there is a notion of oracle interfaces here. So the verifier, whenever you see this green rectangle, it means that it doesn't see the underlying data precisely. It only sees the oracle. It can only interact with them through a specified oracle interface. And these interfaces are, of course, formalized using VCVio's notions of expressive handling of oracle calls and queries. Okay, these reductions compose really well. This is how we can build extremely complex proof systems from very basic building blocks. But also proving that these compositional properties preserve the security properties is a non-trivial task, which we are making progress towards. So that's the general goal and general setting here. I would just show you some very basic definitions of how we model these protocols, or at least this is part of a rewrite that I'm giving to RClip, where I swap out the foundation before with this new foundation that is, say, less stateful and more continuations based. The basic type here is that first you have to specify the protocol structure, and that includes the specification of exactly what type of message is sent at each round. The message can either be public or it is an oracle. And you also have to specify who talks in each round. And so That just means that in every round, you can decorate or you can ornament the spec with the row itself. And this idea of ornamentation also comes up a lot. So you can ornament it with, say, a monad that the prover must do in every round. So prover here, let's say it has one monad throughout. What it can do is that in every step, it can do some side effects in that monad, and then it needs to either return a response and then continue with the rest, or it needs to take in a response and continue with the rest of its computation. So this is just a very clean inductive definitions. There is no inherent notion of state that is baked in here. And it's really just, you look at the protocol structure and you have adversaries with exactly the structure. Okay. And you can also write this out fully if you try to unfold it. The prover for the Schnorr protocol will look something like this. It's fairly easy to specify protocols in this manner. Okay. So that is RClip. The port to this framework is ongoing, and I'm hoping to share more definitive results in the next month or so. The second case study I want to make is that of state separating proofs. So I think the original motivation for SSPs is that it's a way to tame the complexity in very what can be very difficult and complex sequence of games that one would prove about a practical protocols with many bells and whistles. Okay, so I think we would need both the use of good tactics and also good structuring of the games in a way that can make the verification task easier. And so SSPs is a recent techniques for structuring such games, and the core insight is that if you model your games or your reductions as a bunch of small packages that are linked together, then the state separation of these packages can just compose naturally. And separation of the states is very useful and very crucial to having clean reductions. So that was at least the motivation for the SSProof library in COP or ROC, which CACrypt built upon in Lean. So one could ask, well, is SSP, can we actually have SSP, say in VCVio? And yes, we can have it. And I think the formalization of SSP is actually quite elegant. So let me just walk you through what it looks like. So what a package is that it has some list of imports and exports oracles. So the thing in the package can query these imports and exports. It can also iterate over some private state. The private state can be initialized, and the core implementation here is that it needs it's really just a simulation from the exports using the imports. And these packages can then be linked to an arbitrary adversaries with the exports procedure, assuming you have a package that goes in and out like this. And what it does is that it changes the type of oracles that an adversary can query. So this is really, you are linking a package with an adversary. You can also link packages together. So if you think of packages as reductions, these are very ergonomic and compositional ways to link many separate reductions together. And the core feature here is that when you link the packages with different states, you get just the product of those states. And this for both composition and parallelism. So what this means is that the notion of separation that we achieve here is basically by construction. This is separate from, this is fairly different from what SSProof chose to do, which is that we have a global heap, and then packages will have space on this global heap. and you have to make sure that the separation is preserved, or needs to be put in as a hypothesis to almost every theorem that you state. So it doesn't mean that it's not it's more cumbersome. There is now very good techniques using nominal sets to tame this kind of complexity, but I think this presents a different point in the design space that can read to be very ergonomic as well. So we don't just formalize just the theory, we also port it over a non-trivial example. So for instance, the proof of INCPA of El-Gamal, we had it first with just regular tactics and game hopping proofs in VCVio. In recent days, I also ported over the SSP flavored proof for El-Gamal. They are, I think right now, roughly the same. You could think of one as maybe being more easier to read than the others. It's all kind of relative. But the core theory of SS proof is here and is, I think, just represented nicely in 2 slides like this. Okay. So this is basically the core theorem of SSP, which says that when you have many linking of the packages, the linking are essentially associative. You can think of the boundary, you can shift your mental model of the boundaries from one to the other. Okay. The third case study I want to discuss is that of universal composability.
So is it okay if I ask a question?
Of course, of course.
I think I didn't follow how you specified the state separation between packages. Like, at which point do you specify the state separation property? That was not completely clear to me.
Thanks for the question. So the separation happens by default here. So if you have 2 packages, they have different states, then when you combine them, either by linking or by parallel composition, their state is literally just the product of the 2 states.
Okay, so there is no way to express package composition that have shared state in your formalization. That's correct. Is that correct?
Oh, sure. I think they would need a kind of different linking in parallel like operators. It is possible then you would basically recover the heap-based model where things can interact. But for now, this is the thing that I show you because I think it's sort of a separate space in the design.
So in the current formalization, you have all disjunction by construction, so stuff like hybrid arguments you cannot express without redefining the composition.
Can you say again? Sorry.
So, with the current definition of parallel and sequential composition, there are many reductions like hybrid arguments that you will not be able to express.
I think that is certainly possible. Although I don't think it is a fundamental limitations, or rather, it might just require like different structuring of the hybrid arguments.
Okay.
I have a question too. So earlier in your talk, you talked about polynomial functors.
Yeah.
Yes.
And so that's showing up here in Oracle spec or Oracle comp, right?
Yes.
Then you need to show that this package. This morning, Bas talked about how these packages they satisfy the interchange law. So do you then somehow so the package you define here in terms of these polyfunctors, they will naturally satisfy the interchange law because of what you define here. Is that right?
Yeah. So I believe this is what the interchange law says. That you can, when you have 3 things that are linked together, you can think of it as P linked with Q or Q linked with P linked with the adversary.
Okay, right. So the proof is almost like automatic.
The proof of this?
Yeah.
Yeah. It's not a very long proof.
Okay, nice.
Yes. So yeah, we have the core framework, and I think it is definitely a choice in doing state separation like this. Maybe it doesn't recover some of the examples that I think one of you asked about, but maybe it just requires a different way of conceptualizing or thinking about the reductions. So this is definitely something that is open, and I'm very eager to see exactly how far I can push with this formalization.
Right. Thank you.
Yes. Thank you. And here's a third example of, I think, something that I think can be pushed very far with VCVio, which is notion of UC. So UC, introduced by Ron Canetti, is by many people considered the gold standard of cryptographic security, meaning that if a protocol is UC secure, depending on the precise UC model, but what it gets is that you will have security under arbitrary kinds of compositions, unbounded, under all kinds of adversarial threats that may arise, and so on. And one of the reasons I mentioned UC is that this is going to be relevant, I think, for Signal, because if you want the strongest setting, the strongest guarantees for Signal, you would want an analysis in the UC setting. There is indeed prior works on analyzing UC security for secure messaging, maybe not Signal in particular, but a general kind of secure messaging. And in such an analysis, there is a lot of moving pieces and things that we need to state in order to state the core security properties, such as, say, post-compromise security. While this includes global shared state between all the parties, it includes adversaries that can schedule the network messages in an arbitrary manner. And it also includes a possible corruption of any given honest party for a very brief moment, after which the party becomes honest again. So this is a lot of moving pieces and usually very hard to model. And in fact, I take a look at the existing formalization of UCs in prior works, and I don't think they are planning to support this kind of generality. And so when I started thinking about having UC on top of VCVio, the core concern that I have is how do I make a system that can be this general? And the approach here is that we don't start from scratch. We start from borrowing inspiration and insights from other fields. People in other fields have been studying sort of open systems and their interactions for a long time. And here, once again, polynomial functors come up. It is just a very nice way of specifying interactions between different parties, different protocols, and assigning semantics to them. So the core here is that we have a theory of interactions of open systems, where in the theory we have a list of objects that satisfy this theory. And these objects, you can map them, you can link them together, you can have a bunch of objects in parallel. So these are just very basic operations using the notion of polynomial functors as interfaces. Again, this shows up as first as index oracles in VCVio's core foundation. Then it shows up again as the notion of imports and exports of packages in SSP. And finally, the same notion also works for specifying arbitrary open systems. Okay, so with this notion in mind, we can state UC, or at least a version of it, in a very concise manner. So if you have a theory for open systems, if you have a protocol boundary, this is the ins and outs of your protocol, and you have some backchannel for sort of adversarial communication. And finally, you also have a kind of semantics, which says, how does closed systems actually map to probability or sub-probability distributions? Then what you can do is you can define all these classic notions of UC, such as what the protocol is, adversary environments, and then you can have the generic UC definition falls out of the general framework. There's going to be a lot of semantics that is baked into this open theory and the way that we interpret them. So this is really just very general to a lot of different UC notions, and within the UC notions, there can be also a lot of different distinctions in, for instance, scheduling or the corruption aspects that we need to model. Okay. So let me stress, this is something that is very much ongoing work, but I think it is pointing at the right direction for which we can state the most general security theorems for signal that we would like to make. Okay. So let me end towards the end of my talk, let me go back to the question of AIs. So one of the things that astounds me, well, many things astounds me about the state and the progress of AIs nowadays, is that we have PRs made into both VCVio and RClip that is done entirely by AI, either through and usually through like a intermediate human that's prompts the AI, gets a result, and then posts a PR. This comes from both well-known startups such as Harmonic or Logical Intelligence, but there's also some person that we don't know where it's coming from. And that is kind of the really nice thing about formally verified libraries, is that you can have PRs from anyone, and as long as they pass the CI and pass the proof, and that the theorem statements are correct, then we can just merge. Okay. But that's not the only thing. We need to have very strong guardrails, guidelines, and workflows to set up for this AI integration. And what that means is that in both VCVio and RClip, we maintain a very detailed wiki of the overview of the code base and say tips for utilizing it, explanation of how the different pieces fit together, and gotchas or like pitfalls that one might fall into. So this is, I think, very useful for AIs, but also for humans as well. You can just read through the wiki. We have reviews for every PR. The review conditions are quite strict. It will flag every new stories. It will, well, once again, this is all done by AIs. So it will flag for any possible misformalizations or any other problems. I think it's just standard practice, but applied to the question of building a formally verified library. Okay, and personally, I think over the past months, I've made so much more progress by utilizing AI. So one of the things, one of the reasons why I was able to do all these extensions is that AI is very good at doing massive literature search, synthesizing approaches to formalizations, which I can then think about and further refine, and also explaining papers from subjects that may not be in my core understanding. It is also extremely good at metaprogramming, at least for making sort of toy widgets and tactics. But I think here the core is that we don't just rely on AIs for making this, because it can lead to very unmaintainable software. We also need to inject in good intuition, good understanding of tactics in Lean as a whole, and to guide the AI towards writing the right kinds of tactics. And of course, it can fill in very hard proofs. So on this note of filling in hard proofs, I'll give you an anecdote from for recent days. I've been trying to finish the formalization from the forking lemma, which existed in VCVio before, to all the way to a proof of Schnorr's signature. And I do this by basically just giving AI, prompting it in a loop. It has the proof in the original paper. There's a proof also in the EasyCrypt formalization, which actually it has some. The EasyCrypt proof had some axioms which AIs noticed, and they weren't as trivial, or they weren't as trivial axioms as I originally thought. So we had to fill in those gaps as well. And so what happens is that the AI basically blows up the proof. Finally, it did it, but the way that it did so is by creating thousands and thousands of lines of lean code. There is a theorem that is over 2,000 lines of code. And while that is, on one hand, extremely impressive, but on the other hand, I think it would benefit from, I think, a more principled approach at the beginning, where you would plan things out and make sure that the planning is in the good shape before going. What I encountered within this AI loop is that the AI often had to change the proof strategy a lot of the times, because it may state some theorems and then it got stuck in those theorems, and then it realized the theorems are not stated quite correctly, and it has to go back and then do the loop again. So maybe not the most efficient use of tokens, but at least the proof went through. Okay, and another interesting thing is that AIs are trained using on massive data sets, and these data sets oftentimes they do not include the latest tactics. So AIs, I think, almost by default, or maybe this is something that is trainable, and I hope it's trainable. It doesn't use the custom tactics that we built that often. So, for instance, MVCgen or extension thereof of MVCgen that I have in the library, I usually need to manually prompt the AI to use those tactics in order to decrease the proof. So this is just an anecdote from my point of view, but the broader point I would like to make and to talk to you, to discuss with you about, is that in the context of verifying signal, how can we set up the tooling, the framework, the procedures, so that the humans can work best with AIs? This is just a very broad question that I think I contribute a point in the space to. Okay, so let me just give, if I were to make one summary for my talk for signal shot, that would be we should be planning out the foundation from the very beginning. We should not just be trying to get incremental results, which are definitely extremely helpful to validate that we're going in the right directions. But we also need to think about what are the strongest security, what is the dream theorem that we hope to state. And then we build the foundation that is expressive and strong enough to get to that level. Okay. And in particular, I present about VCVio. I hope this talk has made a good case for VCVio. And I think some parts of the library can be ported into CSLib, and some parts might be under, I think, greater a discussion and might not. So whatever that signal shot is hoping to get from a general foundation for formalizing crypto, I think VCVio can provide most, if not all, of that. So we have a expressive oracle handling through connections to an established theory of algebraic effects and handlers. We also have a relational program logic ERGL. There is ongoing work by the Nethermind team to extend this to a probabilistic separation logic called Bluebell. So once that's done, I think it will provide even more reasoning principles for our programs and for our reductions. And we can derive this program logic through a monad transformer stack on both sides in a very modular manner. And we have tactics integration that is ongoing to get the most out of these relational truths. And it has been supporting arclib for quite a while, and there's also abstractions that we can put in, and it actually doesn't have take too much to state these abstractions once you approach it in the right way within the framework. So I would like to end my talk here, and thank you for listening.
Any questions for Quang? I have a question. So I asked earlier about the polyfunctors. Do you think that it's a restriction that you're putting on it's a very specific choice of functor that you're using? Do you think that this is necessary for the foundation, for the formalization, or could you work with something more general, other kinds of functors?
Mm-hmm. So I think it may be a bit of a misnomer to think that polynomial functors are very specific and narrow kinds of functors. They're actually very general. So let me go back to here. I could go back to all the way to like the definitions of oracle computation. So here, for instance, it turns out that if you allow for these general types, what you can encode is a more so-called general notions of free monads, where the functor, the mapping from type to type can be arbitrary, and actually a polynomial functor can represent this kind of arbitrary mapping between types. I can talk more precisely about that later, but I think really the literature and other people have shown that polynomial functors are actually kind of the most general functors, the well-behaved functors that you can find. And there is really no loss of generality, as far as I know, for any problem in cryptography that can't be expressed by polynomial functors. So hope that helps.
Yeah, thank you. Thanks. Oliver.
Hey.
Yeah.
Thanks for all the explanations and all the great work you're doing. I'm curious. So you have some tactics that you use to work with the security games. I'm interested what sort of problems there were here, what challenges, and what potential challenges you see for those tactics dealing with the more complex security games.
Yes. Yeah, that's a great question. Thanks. So I think this is in some sense a sort of a trial and error effort. We have a good reference from EasyCrypt. We know how those tactics are implemented in EasyCrypt. We know how MVCgen is implemented. We both the old and the new versions, which is coming with SimM. And I think when you put all of this together, you will notice a lot of points of consolidation that you can get. So for instance, this is what the relational tactics is built upon, or even the unary tactics, but instead of having propositions as the point in the lattice, you would have general like probabilities or general expectations. So I think extending all of this is a very fascinating task. I think the tactics framework will evolve alongside the efforts to prove the protocol, and that's a really nice thing.
Oh, Bess? Yeah.
So I think this is great work, and we should really talk also together with Alex to see how we can integrate the two libraries. The work on UC is interesting. What I presented a couple of weeks before to my colleagues is a full categorical treatment of UC. So I'll try to present it here in the coming days.
You can do a seminar as well online.
Yep.
Yeah, we will have recordings of all the talks here, Quang. So will be made public on YouTube, the Lean YouTube channel.
Yeah, sounds great.
Okay. Yeah, Cristiano.
Yeah, thank you, Quang. Very nice talk. It seems that something that the cryptographers like very much or need very much is to find attacks. And in the symbolic case, it seems you can just, play with the traces and pretty much like model checking does, something like that. The question is, how do we do something similar? Not similar, actually, because they're quite different models, but how do we find attacks in a computational model?
Well, I think the best answer from my side I can give is that once we formalize the protocol, AIs can be the attackers. So what that means is that we formalize it, we have AIs check against between the formal models and what's in practice. It might show up gaps, and we can try to let AI think about writing the proofs, and in the process of that, it can also uncover unexpected attacks, or at least missing hypotheses. This is something that I've encountered a lot. Yeah.
Okay, thank you very much.
Yeah, thank you.
Okay. Any other talks? Oh, sorry. Questions. All right. Let's thank Quang again.
Thank you.
Okay. Yeah. Thank you, Quang. So, we'll hope to. I think if we have more questions, we will send them to you. Okay.
When we have.
Yes. I said if when
You
yes
said
when
if, I'm
when
sure it's
we
when.
definitely will have lots of questions. Oh, I actually have one last question, which is that you showed this step tactic, and then Sean Ho is not here right now, but he also has like similar step tactics for Aeneas. It would be great
Yes.
if we can see how we could merge that, because
I actually based that upon Sean's Aeneas like implementation. So
great.
It's all very connected. I think we should pull the resources together to make a really nice tactic system.
That would be great. If we can get it done by this week, that'll be even better.
Sebastian's within sight here.
Oh, Sebastian's here. Oh, great. Okay, let's do it. All right, thank you, Quang, again. See you. Bye-bye.